Yannick here? He's not here, I can say whatever I like. He just sort of volunteered me for this talk by writing down my name on the schedule. So on the surface it may look like this talk has nothing to do with this workshop, but I think by the end of the talk you will have been indoctrinated the correct way a little bit to be a little more to appreciate some of the things that are going on in formalized mathematics. So my goal today is to convince you in 40 minutes, okay, I explain how not to believe in excluded middle. So first of all, let's see what excluded middle is. Let me write it down. So I think before we start with an explanation of how not to believe in excluded middle, we have to look at what excluded middle is. Okay? So this is also, I'm just going to refer to this as LEM, law of excluded middle. And it says that for any proposition P or not P. There are so many quips and jokes you could make in every sentence here that we should try not to.
I'll stop. Okay.
Let me do it. Okay, so first of all, let's have a show of hands. Is this entirely obvious? Who thinks this is completely obvious? Yeah, we see. Yeah, okay. Let's be honest. You know, raise your hand. Raise your hand. Okay, yes.
What order you're talking about?
So one of the problems that I think happens when people try to understand constructive mathematics is that it's really hard to understand how the hell, like what, how could you possibly not believe this? Because it's so obvious. And so I will try to explain how to not believe this thing. Okay? That's my goal. Now, constructive mathematics is there we go. It is the mathematics done without this law. Now here is the first point of misunderstanding. When somebody says you do it without this law, people think that constructive math says there is P which is neither true nor false. Okay, that is a common misunderstanding. So somebody says, we're not going to do this, you jump to the conclusion and say, we're going to do this. Especially because the law of excluded middle is sometimes called the law of no third, that there is no third option. And so somebody says, I don't accept this, then you say, aha, you think there is a third option. Okay, so false. Okay, this is not what constructive mathematics is about. Here, this, in fact, this statement, star is constructively false. Why? Well, let's write it down as a formula to say that P, here, where are we? Here, to say that P is not true. How do you say P is not true in logic?
Like P.
Not P. So it says P is not true, and how do you say that it's not false? No. You use classical logic.
I promise it's not.
It's this. Okay? But this is a special case of this, where you take Q to be not P. But this is clearly false. Okay? Also in constructive logic, if you really want to know the details, you can take this, so this is defined as Q implies false. So now you have Q, and you have Q implies false. So just use modern exponents to derive false. So false, okay? So this is not at all what constructive mathematics says. So that's a common misunderstanding, and I just want to get it out of the way. Okay. Also, another point I want to make is, when I say that I don't accept this law, that doesn't mean I can never ever use it. I can use it in special cases that I prove with my bare hands. So if I can prove some particular case of this, it's okay. So, example, for every natural number, n is 0, or n is not 0. That's a special case of excluded middle. We can prove this. How would you prove this? By induction, of course. Okay, let's do it by induction. Base case. N equals 0. Okay, if you assume n equals 0, does it follow that n equals 0 or n is not equal to 0? Yeah. Induction step. What if n is a successor? So it's of the form, say, k plus 1. Can you tell me which of these two you're going to prove? You're going to prove that one. Is there an axiom that says that successors are not 0 in the piano arithmetic? Oh, how lucky we are. Okay. Yeah. So you see, you can prove certain cases of excluded middle, and then it's okay. Right? You just have to be careful. Okay. Now, because I only have 40 minutes, let's get to the point. How not to believe in excluded middle? I will first give you two really bad ways of trying to not believe excluded middle that are common, that I have seen, and they don't work at all. Okay? So here are ways. Here are bad ways. Okay? Failed attempts at not believing length. So the first one uses the fact that they are undecidable statements. So somebody says something like, oh, Cantor's hypothesis, CH, is independent of ZFC. And say, yeah, so what? Well, so therefore, neither true, neither false, something la la la. What they're trying to do is they're trying to establish this thing here, which is obviously false, or something, I don't know. Right? They think like it's a third possibility or something. So, first of all, ZFC very obviously proves CH or not CH. Because it does so for every proposition, because it's classical logic. So this is a non-starter. What I think confuses people is the following. What does the independence say? Independence says ZFC does not prove CH. ZFC does not prove CH, and ZFC does not prove the negation of CH.
It's not contradictory.
Right? Yeah. This is the statement of independence of Cantor's hypothesis. This is not excluded middle. It has nothing to do with excluded middle. It's not an or. Right? It's not of the correct form at all. Okay? So it's irrelevant. Bad attempt. Yes?
What about IZF?
What about IZF?
Well,
ZFC doesn't prove these things, IZF is weaker than ZFC.
Yeah, but IZF doesn't have excluded middle, right?
Exactly, so
Yes.
it's obvious if there's disjunction elimination or something like this. So in IZF, if you could prove this, you could prove one of the two, and you know you can't, so.
These are external statements, not internal statements.
Wait. What?
Okay, you're saying ZFC blah, that's
Yeah.
obviously.
So you want, but first of all,
I
here or here? Which one are we talking
I
about?
want something else entirely. I don't want to talk about ZFC, I want to talk
Yes.
about IZF.
Yes.
So if you write down the same thing again without.
This one or this one?
This is the first one.
The first one.
With IZF instead of.
Yes, so this is the case, okay?
So because this is constructive logic, if you can prove that, you can prove one of the disjuncts. Exactly. So
Right.
now you have-
IZF does not prove this.
Exactly.
Yeah, but IZF is an intuitionistic system which does not validate excluded middle. So if you believe in IZF, you can just walk out the door. So this is not very clear,
Okay.
right?
Yeah.
I think to defend a bit this point, I think they're not saying, well, when someone says that the counter hypothesis, counter argument is not excluded middle, what I think they are saying is that you should expect that a system that proves a disjunction proves one of the disjuncts, which is what Professor is saying about
Right.
IZF. So it's not such a bad argument, it's just misdirected.
Sure.
My argument was just like you want a concrete P. Here is a concrete P.
Yeah.
Anyway,
It's a matter of
sorry
We
for
were defending a straw man anyway, so it's okay.
Okay.
Okay, here's the second best but bad attempt, which has been proposed seriously, and for me personally, it never was worth anything. If anything, it's just sounded dumb. It's called Brouwerian counterexamples. And I'm mentioning this one because you might have seen texts that try to convince you not to believe in excluded middle, that use this kind of argument, and just thought it's bollocks. Well, I agree with you. Okay? So it's something like goes, I think this one is about what we know. Now, there is intuitionism, Brouwerian intuitionism, which is a serious philosophical position in mathematics, where the things that I'm going to badmouth right next are discussed seriously, and they do have their proper place in weight. But my point is that the naive understanding, is that my phone? No. The naive understanding of Brouwerian counterexamples doesn't help at all. So here is the naive one, okay? So the naive one goes something like this. We do not know whether, now something like 7777777 appears in digit expansion of pi. So how could you claim that 7777 either appears or does not appear in the digit expansion of pi? And you're supposed to be, after this, you're supposed to say, yes, I do not believe in excluded middle anymore. Does not work for me at all. Okay, why? Because I do not equate knowledge with truth. Right? You have to develop an understanding of mathematics where knowledge and truth are much more closely linked. And for me personally, that doesn't work. So I just mentioned that this is one possibility, and that you don't necessarily buy it, and I don't either. Okay.
Like, does it relate to the previous one? Like, isn't showing that it's undecidable?
Yeah, it's not totally unrelated, because to have a proof is to attain knowledge. And so this is saying somehow it's not, the knowledge of CH is not attainable through the mathematical method. So it's a bit linked to that, yes.
It's much more, it's much stronger.
Yeah.
it occurs at position 3,364,000.
There you go. Okay.
But we do know know, right? It isn't by like a normal number.
No,
we
we
don't
don't
know.
know if there are any we don't know of any specific normal numbers. No one has exhibited a normal number.
Sure about that?
Nah, so
You
artificial.
could just artificially make one up.
artificial
In any digit base. Normal means in any
Oh, it's
base.
normally any base. Okay. Yeah. Okay. Good point. Yes. Okay. So now let's try to not believe Lem. Okay. To explain what we're going to do, we have to go back to ancient Greece. How would you explain to Euclid not to believe in the parallel postulate? You have a geometer who has been trained to understand that there is exactly one parallel through a point to a given straight line. And it is completely and entirely obvious because you can see it with your own eyes. But now you have to convince them that this postulate can be questioned, that it could be understood to be false somehow. What do you do?
Show them a globe. Show them a globe.
Show them?
A globe.
A globe. Okay. Yes. So you would say, show them a globe, and then what?
Show that the latitude, show that the great circles.
Okay. Yes. Okay. I'll be Euclid. Yeah. Why are you showing me these circles?
Well,
They are not straight.
yes, but
Show that
it's
they
not
satisfy.
one of the axioms of geometry that lines are straight. And then it satisfies all of your axioms.
Okay. So what you're going to do is you're going to convince me. What you're going to do is you're going to find a model of geometry so that means you are going to bend the meaning of straight line, literally, such that all the postulates will hold except for the parallel one, but all the others will still hold. That's what's going to be convincing. Maybe, hopefully. I think that would work, right? So we're going to do the exact same thing. But what is it that we need to bend? We need to bend logic, right? We must, this is more fundamental, it's trickier. You have to bend logic, okay? So somehow you need to come up with understanding of logic that is going to validate all laws of logic except excluded middle. So, okay, we need to do something, and it has to be radical, right? So here, it's radical. The lines are not straight anymore, right? Or there are other models where lines are somehow miraculously planes, right? That's another one that works well. So that's also pretty radical because you're increasing the dimension of line. Like all your life you thought line is one-dimensional, and now suddenly it's two-dimensional. This is upsetting. But I think it's only upsetting for a little while, and then after that you realize, oh, this is actually kind of cool. Okay. So let's try to do that, and we're going to do it in several steps. The way we're going to do this is, so we have to change the things that appear in excluded middle. So proposition, what a logical formula is, and then the logical connectives and what the proof is. We have to change all of that. This can get a bit technical to do it precisely, and of course I'm not going to be technical, I'm going to explain the ideas. But I think once you understand the ideas, you can more or less work it out by yourself after that, okay, how it works. Okay. So my first step, I will do it in 3 steps, and the first step doesn't work, but it's on the right way. It goes in the right direction. So step number 1. Okay, the steps are maybe a little bit weird because we are bending lines. Okay, so the first one is that I'm going to say, for some reason, that a proposition. Wait, I'm going to want to keep this one. Okay, so to make sure, proposition is a sub-singleton. What is that? So that's a set with at most one element. Okay? So that's a set. S is a sub-singleton. Okay, when the following holds. For all x, y in S, x equals y. Why did I write it this way? I wrote it this way to show you that I don't have to say it's either empty or not empty. Okay? You can just avoid that. This is the correct way to say that something is a sub-singleton. And now, P is true is going to mean P has an element. Okay? So now you will tell me the correspondence. False is which set?
P has
P implies contradiction as an element.
Empty set.
no.
Oh, sorry, false is the empty set.
False is the empty set, right? It doesn't have an element, so yeah, okay.
No, wait. False is the proposition because your propositions are sub-singleton. So it's
Yes, so whenever you want,
false is the proposition that that sub-singleton is equal to.
it's this set. It's not the proposition that this, so to say that P is true is to say that P has an element. So now propositions are sets, and you discover whether they're true or not by investigating whether they have an element.
Oh no.
Yeah? Okay? So false will correspond to the empty set. Everyone with me?
Yes.
Okay. So true corresponds to, well, some set with an element. So we need to pick some canonical representative. So give me anything.
A dot.
Hmm?
A dot.
A dot. Okay, I'll make it a large dot, so there's no doubt it's there. Okay, it's a bullet. Yeah, but we also need to do logical connectives. So, I need a set theoretic operation such that it corresponds to this. So it needs to be a set theoretic operation such that when I combine two subsingletons, the combination will have an element if and only if they both have an element. What operation could that be?
The union and quotient by the total relation.
But then if one of them has an element and the other one doesn't, what you described is before.
The intersection? Cartesian product.
Okay, I heard two. Cartesian product and intersection. Let's investigate them.
Intersection.
Which one do you prefer? Well, does this one work?
Yes.
I think so, yeah.
Does this one work?
No.
Why not?
Because it's empty.
Because
They have different elements.
No,
they could both be singletons, but they could have different elements.
Yeah.
And then there will be disjoint, and then you'll get the empty set. So this one doesn't work. Okay. We'll do another one. Implication is what?
Functions.
Functions from A to B. Some people have read literature before. Okay? Okay, you have to think a little bit about this. I torture first years, I teach logic and sets, I torture first years with functions into the empty set and from the empty set. So, which one do we need to worry about? So if you has an element and this is empty, can you have a function from something that has an element to the empty set?
No.
No, you cannot. So that one works. You can think by yourself. It works in all ways. So it's going to work. It's okay. Okay.
Are you going by cases on whether it's empty?
Yes, I'm going by cases. So I can consider 4 cases here. That does not prove that this will work. That is an intuitive justification for why this could be the right thing. To prove that it actually works, I would have to know the inference rules for implication, and then I would have to map those inference rules to suitable operations on functions And then I would know that it works. And no consideration of cases, right? It can be done, but not in 40 minutes. Yes?
Is this construction going on in classical mathematics?
So far, yes. Yes.
Well, you just said that you don't need cases, so.
To humor me, can you write it as b to the power a?
Sure.
So I'm a happy
It's
person.
also written sometimes like this. Both.
Thank you. This is for the YouTube.
Yes. You're going to post comments with jokes?
No. I never post comments.
Okay. You mentioned or.
Disjoint union.
Yeah.
Okay. Oh, stay with him. Does this work?
No.
Why not?
Inhabited.
Because we could get two elements.
Quotient by the total relation.
So now you need to squish them together. So, okay, which will it be? Are we gonna squish them? Or are we not gonna squish them? We have two possibilities. We could at this point squish them. That leads to one possibility. There's another one, which is step number 2.
Change the definition.
Change here to, hey, how about any set? Why do we worry about having just one element? Like, what's wrong with that? Why not just have any set? It's a set, any. And then you just look whether it has an element. What do you care if it's got 15 elements? It doesn't matter, okay? So does it still work? This still works. This still works. Does this still work? Does this still work? And this works also, and we didn't have to have any quotients. Okay?
Couldn't you use the union? Couldn't you use the union?
Yes, good question. Could it be union? It could. It could be union. The reason why we would prefer not to have union is because it doesn't generalize as well to other settings, where you don't want sets here, but maybe you want spaces, sheaves, whatnot, la la la. Then this is going to work better because you know what this is going to be. This is going to be a coproduct. Union, you can still pull it off, and so let me just say that you can still do it, but at this level of explanation, we see that both would work. Okay? And we don't necessarily want to get into reasons why you would prefer one over the other. Yes?
Why do we need the disjunction of propositions to be a proposition?
What?
Why does it have to be a proposition?
Because OR is part of logic. I don't know how to answer the question. I mean, OR is one of the standard logical connectives. We want to be able to interpret it. Is that good enough? Is that an answer?
Sure.
Okay. So we also have, how about equal?
We changed the system now.
Yeah, sure.
Okay.
You don't have to worry about singletons
Yeah,
anymore.
but what are terms?
What?
What is
You
lowercase
just
a?
wrote an equation.
You have two things you want to know whether they're equal.
We were in propositional logic.
So I give you two things, A and B, arbitrary things. You just have A and B, two objects. Now you have to have a set theoretic. Give me a set theoretic operation that is nice, whatever that means, and it's going to give me. Let's do it with singletons still. Let's see if you can pull off singletons. Singleton if they're equal, empty if they're not equal.
Singleton A intersect singleton B.
Singleton A intersect singleton B. Would that work?
Yes.
If they're equal, you get a singleton. If they're not equal, you get empty. I considered two cases. Okay. Yeah. So there's just one more, which is exists. So now you have to imagine what will happen is, we also have for all. I didn't know. Okay, we have exists and for all, and I ran out of space, which is a bit unfortunate. So let me do these two over here. How this is fake.
Many of them are.
This is less fake. So for all and exists are still there. So let's see. Exists x in A S such that A of x and product x in S such that A of x.
You should write sigma.
I think you just.
Spoil the result.
Yeah.
Well, the result?
For the for all.
Then you should write sigma.
Ah, sorry. I think this is what they call a Freudian slip. You will never know whether it was planned. Okay, there we go. So,
Some.
what are some candidates?
Some.
Well, here's going to be a similar dilemma as here. You could take unions or you could take coproducts. Let's take coproducts. So a coproduct of a family, like that. So what you do is the way you imagine this is here. Okay, let's be a little bit more precise. Here, S is a set, and A is a map from S to true false. Here, S is a set, right? Because it's a propositional function. Here, S is a set, and A is a map from S to set. It's a family of sets. Just so that it's clear. Okay? Yes?
Shouldn't it be a proposition? Just to say a set here, so the function from S to
No,
set.
this is the logical side where we haven't interpreted things yet.
So the true false is prop.
This is prop.
Yeah, I call it prop.
Okay.
For people who think that prop is something other than true and false,
Well, is it something that
it's prop and the definition is opaque. You're not allowed to look outside.
Don't you think that? Because otherwise you would have excluded middle. By induction.
This is the traditional logic side. Don't worry about it. We worry about here we're going to get excluded middle. This is classical logic. The question is, will we get excluded middle on the other side? That's the question. So, yes?
The subset, just elements in S that satisfy A, would that be a definition of your exist?
Say again?
The subset, just the set completely.
So there's a third possibility here, would be the set of those x's that satisfy A.
Same thing, right?
It would work.
As a morphing.
Would it? Yes, it would work, yes. It would work. So we have three possibilities for what we could stick in here. That's at least one 5-year research project. And 3 PhDs. Okay, pi. But to be serious, you are exactly discovering the topics that were of interest when these things were being discovered by constructive mathematicians. And you will see these phenomena in your favorite proof assistants as well, and it'll be easier to understand why they babble about having two exists, the strong and the weak, and la 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 and something, and why in Coq sometimes you write a bar and sometimes you write an ampersand when you define the thing that looks like a subset but is not a subset. And there are reasons. Okay, so here we're going to use the Cartesian product. Okay, because you want for every x in S, you want to give an element, okay? So, what happens to excluded middle? Now, ignoring size issues, what did we do? Well, let's write down excluded middle. For all P in prop, P or not P. What is now the set theoretic way? For all,
You didn't define not.
I didn't define what?
Not.
Oh, yes, thank you. I forgot not. So not, oh, here's a line.
Yeah, the complement.
So not A, I will use the intuitionistic trick, is empty set to the A, which is just encoding not A. I encode not A as functions from A into the empty set. Let's naively think about the two interesting cases. If A is empty, then I will get functions from empty to empty. Is there a function from empty to empty? Yes. Okay, so not of false will be true, and not of true. If A has an element, this is empty set, so it's okay. So that's how negation works. Okay? So let's go back to the excluded middle. For all A in set, whatever that is, A plus not A. Okay. What would, so well, now we, instead of asking, is this true, we ask, does this have an element? Okay, so what does this element do? So this is an F, it takes an A, and then it needs to either, okay, so now I need notation for coproduct. So when I have a coproduct of S plus T, so let me write the elements as iota 1 of little s, if S is in S, and iota 2 of little t, if t is in t. So just to know where I'm tagging them with the canonical injections into the coproduct. So this is going to be, well, okay, the other one is easier. It needs to be iota 2 of the identity on the empty set if A is empty. Right? Because if A is empty, then we're going to go here and use the identity on the empty set. What do I do here?
Apply global choice.
Okay, iota 1 of 1. Of what?
The global choice function of like the.
Okay, you want to have a magical function called choose. Ah, yes. Oh, Hilbert. How smart. He was a smart guy. Epsilon of A. There we go. What is epsilon? Epsilon is a magical thing that gives you an element of A. If, yeah. So in set theory, to have this epsilon is known as global choice. So we failed. Because all I did was, after all of this, I replaced excluded middle with global choice. But anybody who's been raised to believe that excluded middle is obvious is not really going to worry about global choice. Let's be honest. I mean, they will also believe in the axiom of choice, and that's a minor detail choice, global choice. Just delete the word global. It's obviously true. So I think we failed. We did not succeed. But we are on the right way.
Can you define?
We need to do something to prevent that hack there. Okay? So, okay, there will be two ways of doing that. One, which I think would not be very in the spirit of constructive mathematics, is to construct a model of set theory in which global choice fails. That's not going to be, right? I mean, then we're done. So we could do that, okay?
Yeah.
But is that easy to do? Construct a model of set theory in which choice fails?
Let's go ahead, right?
Didn't somebody get a Fields Medal for that? So maybe there is a, right? So maybe there is an easier way. So, by the way, to get rid of these size issues and to not have to think about set theory, we could also just try to invalidate a particular case of excluded middle that is easier to think about. Okay? So consider the instance of len for every x in R, x is 0 or x is not 0. So let's rewrite this. Pi x in R singleton x intersection 0 plus empty set to x intersection 0. This is what we get. Okay. What would this f do? Well, f of x is going to be x, 0, if x is 0, and it's going to be computer science getting in the way there, it's empty set if x is not 0. For all practical purposes, this is what? Well, this is a map. So you could think of it as a map from real numbers into 0, 1 if you declare this to be 0 and you declare this to be 1. So it's like a map into booleans.
Shouldn't it be iota 0 instead of set of 0?
This should be iota 1.
Without the set. Without the set, I think.
Without this set?
It should be in the set.
Oh, it should be an element of the set. Yes, thank you. So iota 1 of 0. Thank you.
Just for the YouTube.
Yes. And if we are too very keen on ZFC, you will think this is the empty set, and you will think that this is the empty set. And it's pretty nice. Okay, so we need to get rid of this function. What?
Wait, no, that's not the empty set.
What?
0 in the real numbers is not the empty set.
Of course it is.
No, it's
Von Neumann told.
No, it's the set of all.
Oh, okay. Let's not go there. Okay. So we need to get rid of this function. Now, as I said, this is a function. What does the graph of this function look like? At 0, it's 1. At 0, it has one value, and everywhere else, it has a different value. It is discontinuous. It is not computable. Because if I give you a way to calculate arbitrarily good approximations of x, I give you a box. You can ask the box for as many digits of x as you like, or better, good enough rational approximations, so they could go like up and down a little bit. And now you're supposed to calculate the output of f of x. It could be problematic. So in some cases you will be lucky. Like if you're here, you will calculate a good enough approximation and you'll say, oh, I'm away from 0, I know what the answer is. But if your approximations don't tell you what's going on, then you will not ever be able to actually output the other answer. So that points the way forward, which is replace set with space. And then replace functions with continuous functions. So, do we have empty space? Yes. Do we have a singleton space? Yes. Do we know how to make Cartesian products of spaces? Yes. Do we know how to make function spaces in topology? Compact open topology? Maybe. Does it always work for all spaces? Okay. That's one more PhD, right? Right? See how to be a mentor, right? So why don't you figure this out? Come up with something that is like spaces, but it's got exponentials.
When you say space, do you mean topological space?
It's a PhD, it's open-ended. Whatever they do, good enough, we accept it. The point is, but we know what the criterion is. At the end of the day, this function shouldn't be there. Right? So at least for nice spaces like real numbers and discrete space on 2 points, the functions should be the continuous ones, then we're okay, then we broke excluded middle. So one reason that excluded middle can break is because it forces you to make a discontinuous choice. That is your first hook to understand how excluded middle can break. Because you say, everything I do needs to be continuous and topological, and there are discontinuous cases of excluded middle, and those will not work anymore. And now you also understand why this works. It's because the natural numbers are a discrete space, so it's not all going to be continuous. The other one is computable. Well, then we replace set with type. This is why we're here this week. Type. So then, these are types. Do we have a unit type? Do we have an empty type? Okay, do we have Cartesian products of types? Do we have function spaces in type theory? Do we have products in type theory? Yeah, we have everything.
Equality?
Equality? That's also a PhD, actually. Actually, no, that one is more than PhD, because that one, right, is Martin Löf, Streicher, Hoffman, Voevodsky. So those guys already had their PhDs when they did equality. Audi, Warren, yes. Am I forgetting anyone at this point?
Cubical type theory people.
Cubical type theory. So this is actually now recent research. Right? We're getting
Observational
Sorry, Steve.
type theory, higher observational type theory.
Yes. So equality can be a bit tricky. And in fact, when you teach type theory, equality is kind of a stumbling block often, I think. But why? In type theory, so in type theory we don't have real numbers, so we should look for a different kind of example. So you can take a different example. You take what's known as LPO. So you replace the real numbers with the counter space. So then you ask, is it the case for every sequence of digits, of bits, that alpha either equal, I'll write, this is called WLPO, it's easier because it's directly an instance of excluded middle. Is it the case that it's the zero sequence or not? Or it is not the zero sequence? Yes? And in type theory, you have an important feature of type theory. If you can write down some function in type theory, it's going to be computable. So, is there a computable map that given an infinite sequence like that, it will decide whether that sequence is always zero or not? Now, this is going to depend on details, on how these things are represented. Are we working with Turing machines? Are we working with lambda calculus or Python or whatnot? But computability theory has the answer, and all reasonable models of computation have the same answer. No, you cannot do this because otherwise you could solve the halting problem. So that's another reason why excluded middle fails, is because you commit to doing everything in a computable way, but sometimes excluded middle wants you to make a non-computable decision, and that's why it can fail. Okay?
Professor, could you do constructive semantics like directly with Turing machines?
With Turing machines, that is a good answer. Okay, so that's a good question.
It is
Yes.
true if it holds or whatever.
No, not quite. It's a little more involved, and it's called the effective topos. Okay? It's a little more involved. So, but it is the idea that validity is witnessed by Turing machines doing things. So, in order to say that, instead of saying has an element, does not have an element, you say there is a machine that does this, or there is no machine that does this. So there is no machine that can decide this, therefore it's not valid in the effective topos. That's the reasoning that you take. It originated with Kleene, and the buzzword you want is realizability. Before you try to digest the effective topos, it's easier to look like at the same thing but scaled down, like arithmetic only. It's easier to understand. Okay, so any more questions?
Isn't this also your first thing? Like, couldn't you take doable instead of what they decided?
So are you saying so we could maybe interpret everything by saying true means provable?
Something like
Yes.
that.
So that I think is also a fairly serious position in intuitionism, that you say, because there's going to be a spectrum of possibilities, because you know what you know versus what you can prove is kind of related, so you can investigate this. I personally have never quite I cannot identify with that position. It doesn't quite make sense to me to equate truth with probability. I think this is weird.
But can you create a formal model?
Yeah,
But you could possibly create a formal, so what you could do, well, yes, it's a tactic model, right? So what you could do is you could take a logic and create a syntactic topos out of it, and then ask what happens in there. And that would be one other possibility, yes, definitely. Once you have two of these, right, then you know that topos theory is something is going to happen, right? And in fact, there is a rich, so there's this, I come to my last point. Why would you not believe in excluded middle, other than that it's fun, okay? Why would you work without it? Well, because we are discovering many different interpretations of logic right? So, are they relevant? Well, is non-Euclidean geometry relevant? Was it relevant when it was first discovered, or was it only a curiosity that somebody put in a drawer and was afraid to publish it so that they wouldn't be ridiculed? It was. Is it relevant today?
Programming GPS. Yes.
Yeah, GPS, to start with, right? Yeah, okay.
One fans.
Bunch of things. So, I would be very, very careful about pronouncing any kind of math as irrelevant. I would be very careful about that. After that, it's maybe a combination of fashion and what actually is useful at a given point in time. So if people who are studying Grothendieck toposes find good applications of logic, then they will be interested in non-classical logic because their toposes are not classical. So there will be the usual development of mathematics. But I think the first step to make is to actually try to believe that it's possible. And I hope I convinced you of that. Thank you.